All right. I'm RedPantz, and this is kind of an introduction to vulnerability analysis. And I'm doing this presentation. Volume. I can't. I've been drinking and smoking for 48 hours. I can't talk any louder. No. Is it? Can we hear? We good? We good? All right. This is introduction to vulnerability analysis. And I'm doing this presentation because when I first started doing some reverse engineering, there was quite a few little things that you just can't open a book and read about and learn what to do to get you started. And that's why I'm going to do this presentation here, and hopefully someone can take something away from it. But I don't have any slides because I made slides before and I realized they reek really bad. I'm not going to try to teach anyone here assembly, be it that A, it would take too long, and B, I'm really not that good at assembly myself. We're going to be doing IA32 architecture, which is Intel processors, 32-bit. And I guess I'll go over some questions that I think I've been asked before. One of them being, why are you only doing this for Windows? The general answer is it's vast market share. Majority of malware and exploits these days are going to be for Windows operating systems. So the tools and the techniques used and the data structures are all geared towards Windows because that's just how it is generally. Throughout this talk, if I'm going too fast or you don't understand something or I'm not explaining something right, just throw a shoe at me. It's inside joke, but just throw a shoe. I'm going to start here with a very, very simple example. Oh, I meant to say too that I'm just going to go over two what you would call vanilla Stack Overflows. There's no stack protection. There's no stack cookies. That stuff. So this is not commonplace in most of the vulnerabilities that happen today. Very rarely do you see some vanilla Stack Overflow happen in a decent piece of software. Those have usually been hunted to extinction up until now. But I guess the first thing I'll do is I'll show you my little diagram that I made. Yes, I made this in MS Paint, and yes, it's very shitty. But this is one of the things that really helped me understand how a stack-based buffer overflow would work. Because so many different diagrams show it in so many different ways. Some show it long ways, some show it, lowest memory address at the bottom, highest memory address up top, and vice versa. I think these little crappy arrows that I made helps out a bit. So here's basically how a stack frame is set up. When you call a function, the return address is put on there, and right here, this up here are lower memory addresses, and these are higher memory addresses down here. So you call a function, and the first thing that gets pushed on is the return address, which is what you're going to use to pretty much exploit the system. The next is the saved EBP or frame pointer. Hardware! Yeah, that guy rocks. Oh, dude, I got one, man. All right, sweet. And then after that comes all the variables. You'll have some location in memory up here that say we're copying strings, and this is where that goes. And this little arrow here, I think, is the most useful. I actually stole this. I created this myself, but I kind of stole the whole thing from a paper that the EI people wrote. But you look at it, and this is the way the overflow goes is down. It goes towards higher memory addresses. So you'll see data being written at higher and higher and higher memory addresses. And that's, like I said, I did this because I thought that it would be useful, and that's one of the things I didn't realize. Like I completely understood how a buffer overflow worked when I first started, but I didn't fully understand how it would look in memory. And I think visualization helps for me. So maybe it helps for some other people. But this is the general stack diagram, and if anyone wants these things, once I'm done, I can put them up on the internet tubes, and you can get them via internet truck or however you get things on the internet. Oh, I'm sorry, it's not like trucks, right? It is a series of tubes that Al Gore created. Correct? Are we all in concurrence with this? All right. So it's let's go, because that's the fun part. This right here is your classic example of a stack-based overflow. You see some things wrong in here. They have a buffer of 10 characters, and they're just copying the first argument from the program in there, and we'll just say it's someone's username. And if you do it here, maybe I don't have it compiled. Okay, it may or may not do something. We're going to load up Ollie debug, and I really like Ollie. It's free. You can download it. You don't need to install it. It's one executable. You can put it on any system that runs Windows. Is anyone here familiar with Ollie? Oh, awesome, sweet. Okay, so generally, I stole this whole background thing from a coworker because it's originally white and stuff, and it drives me insane, makes my head want to explode. So I need black on there. But the first thing we're going to do is we're going to open our executable. Yeah, now we're talking. All right, I think work. All right, here we go. So we're going to open our example. There you go. You have your assembly window over here. These are all your registers. This is your stack window, and this is the memory view, and you can dump memory. So, be it on this one, it's abnormal. We have the source code. There's not too much there, that we don't understand, and we see that we have to type a username as an argument. But let's just run this program here. Yeah. And okay, it terminated. One of the things to do once a program terminates or throws an exception is to look at the call stack, and you hit this little K button here, and it shows you the call stack. And most people who program C first know that the exit code 1. That probably means something messed up. I don't know what this is, but an interesting one here is you see a module entry point. And be it this is a small program, it's probably a good place to start looking. So you hit enter on there, and okay, it's some unconditional jump, and you can hit enter again, and it takes you there. So we'll set a breakpoint by pressing F2 on that, and we'll restart this program again. Okay, and then did it run? Okay, we ran it, and it hit our breakpoint, which is cool. So that's one of the first steps. If you can get your breakpoint hit, then you can go along. And we can single step through these things. And like I said, I'm not going to go through the assembly of this. You can learn that on your own time, or I'm not very good at explaining it anyway. But you see it does something. We have this is apparently is the window that it's running. And there's really only a few basic instructions that you have to realize. Okay, well, it ended there. And comparisons are one, and branches are other ones that are very important. So we have a breakpoint in Ollie that we know is the beginning. We can run the program again too in our window, and we'll see what happens. And it says it needs a username, so it's giving you some usage error. This is when I'm going to use another tool called IDA Pro. Is anyone here familiar with IDA? Sweetness. All right. IDA's not free. I think you can download a free demo. What's that? It's. I'm sure if you want a copy, you can acquire so. For legal reasons, I'm not going to recommend doing things like that because that's wrong. We're going to use IDA to crack open this binary here, and there we go. Takes a while on this crappy laptop. You can open up this example, and okay, sure, we're going to hit enter for all the default. No, what's going on here? I'm blowing it. I'm losing this presentation. Try this again. Okay. It loads the program up, and we see that it's doing its thing. You see the little yellow light. That means it's not done. When it turns green, that means it's finished doing what it does. But as it's doing this, we can safely assume one thing, and yeah. Am I losing track already? Yeah, I know. If you would have spilled my beer, I literally would have just sat here and cried for the rest of the remainder of my presentation. You can do one of the easiest things to do is look at the strings in the binary and to determine where things are and what's going on. So we know just by running our program that this program says usage classic.exe username thing. So we'll go to the strings window, which is here. I like to sort them by alphabetically off the bat, and then you can just type what we saw. So it was one of the caret type things. Well, there you go, and you see that looks very similar. It's a format string, and that looks similar to what we saw the error in the program. And you can hit enter on this, and it takes you somewhere. And this is honestly why IDA is actually useful and not like object dump does a really great job of dumping you the assembly from a binary. But when you hit Control X on something here, it gives you cross references. So it's going to tell you where in the binary that this string is referenced. And in our case, we're lucky because there's only one place. A lot of times you'll see hundreds, and it's not useful then. So you hit enter on that, and you see, oh, okay. Apparently, it pushes these things on the stack, and then calls fprintf. And if you're familiar with C, it's a print statement that you're printing out somewhere. Here I'm printing it out to the standard error. But if you scroll up here, you can generally see like, okay, this is the main function. And we found the same thing in Ollie. If we restart, try to restart it. We see that we kind of set the same set a breakpoint, the same memory address in Ollie as we have about here. I mean, it's not exactly the same, but I'm just trying to conclude that you can find an entry point into a program either by doing runtime type analysis that we did using Ollie, or if you're lucky, you can open it up and do static analysis with IDA Pro and find a good entry point. And now we're going to move on to how exactly you determine how big the buffer is that you're overflowing. And this is very important. Question. True. Minneapolis Airport bathroom stalls are responsible for the majority of buffer overflows on the internet. It's a fact. You've heard it here. It's a fact. So, as I was saying before I was so rudely interrupted, was you need to find the exact size of the buffer for reasons. Whether you're writing some kind of IDS signature or if you're writing an advisory, you sound like, oh, damn it, Tom, or for some unknown reason you were crafting an exploit. You need to know the exact size, and a lot of the old buffer overflow tutorials will tell you, like, yeah, pad it with a no-op sled in front and then repeat the memory addresses. I find that a shitty way of doing things. It's a half-assed way of doing something. You want to craft an exploit in a way where you know what place that the return address is, and you know what to write there. It shouldn't just be this big NOP sled shellcode repeated memory address thing. That's shitty. Like it's old and shitty and it sucks. And you really can't do that. What's that? Yeah. Drink? My mom would be proud. Yeah, so now we're going to go through this and find how big the actual memory buffer is. And we kind of know that, obviously, it's 10 in our program, but I really like breaking open binaries and looking at them just because it's interesting me. But you get to see more things happen here, and you'll understand why. So as we go, it does some things here, like I said, that I'm not trying to get into. Do you see here it's comparing arg0, which is the first argument passed to the program, to 2. And if you look in our source code, then you see the statement right here, if argc is less than 2, then print this error. And in assembly, it's that right there. Can you see that I highlighted it? All right. Because I can't see it on my computer, but it looks like it's okay up there. And if it's these two commands are very useful to know. These are comparison, and this is a jump greater than or equal to, and it goes to some memory location. So we're going to go there, and as we go through here, luckily Ida loaded the debugging symbols for this program, and we see we have a stir copy, which in our program, bang, right there. I mean, we know for a fact that this is vulnerable. So this is where we need to be. And you have to know the order in which things are pushed onto the stack. And here, ECX is pushed last. And if you know string copy, it's string, the order of the function signature is destination and then source. So you're copying from here to here. Actually, it should look like this: from here to here. But so it looks like ECX is where we're copying to. Not only because it gives it a var underscore name, which is a stack variable, and B, we see arg4, which is the second argument past the program, is put in EDX. We can definitively say that ECX is our destination buffer. That's where things are getting copied to. Is everyone with me on that? Sweet. Okay, so and it calls string copy. When you see what's loaded into ECX, it's EBP plus var c. And you can hit enter on var c. This is another thing that IDA is really good at, showing you the stack representation of what's going on. So if you hit enter, you can see that this is how the stack's laid out. And there's var c, and down here is going to be our return address. Thank you, Tom. Now, if you open up my favorite Windows tool, Calculator, and put C in there, C is this hex representation of 12 decimal. Okay. And at first you think that's weird because you have a character array of 10. Why would it be 12? And the answer is it's the compiler optimizing your source code to be 4-byte aligned. It's easier for it to always be 4-byte aligned. We're going to test our program just to prove this fact. Is we're going to do classic, then we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And theoretically, this should overflow the buffer because we made a character buffer of 10, and it doesn't. But we'll do 12 and one more just to be short, 13. And you get your little Windows thing and looks at the data. You can view the technical information, blah 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 blah. But I'm just doing this example to show that you can't. You know a very very good number for the buffer size if you have source, but you want to make sure what the compiler actually did to the source code to completely verify what what size it is. I mean, if you're writing, say, an exploit or an IDS signature, you may be able to use the number 10 and fool around and get something to work. But I personally like knowing for a fact how big things are. Having definitive knowledge of something is really awesome. And I've researched some bugs that other people did, and they're saying the buffer size is 10. And after I research it, I say, well, you can exploit it at 10, but you can still crash the program at 8. And I think that matters, especially A, if you're writing exploits, or B, if you're writing some snort rule for something that if you don't have the right number, it doesn't work. And it's a half-assed way of doing things, at least in my opinion. Everyone drink. Drink. Okay. Who wants to go through a real-world example now? Yeah, I will, baby. Yeah. All right. So we're going to close this garbage. And this is really what the presentation is about. That first one was just a warm-up to kind of show you the basic concepts. And this one is how to actually do it. So we have this security focus article here. And it says, mini-share server remote buffer overflow vulnerability. We're going to pretend like if I don't click that exploit tab, there won't be like 10 exploits there, because there is, and this is really old. And we've contacted the author of this program and asked if it's cool if we use it in presentations and whatnot, and he was like, sure. So I'm not doing anything illegal, just for the record. Is that on? Did we record that? Okay. All right. No, seriously, let's start the legal shit. All right. So, mini-share server is reported that mini-share is susceptible to a remote buffer overflow vulnerability. This issue is due to insufficient buffer boundary verification prior to copying user-supplied data. Oh man, the threat con level's at 2. Is everyone worried? I'm fucking worried. In Germany, the internet is better. This is generally the kind of advisory you're going to see. It's very ambiguous. You don't know very much about the product. Wow, a buffer overflows somewhere. Well, fucking thanks. You don't know what it is. And this gets to be the fun point. You get to use your Googling skills to figure out things, which is amazing. Like, it's amazing how much information you can find on something. Just obviously, I mean, we all know just by Googling stuff, going through news groups and whatever. But I'm gonna cheat here, and I know mini-share is this HTTP server where you can just throw files on it and share them with people. But we're gonna go off that, and be it that it is HTTP, a good place to start is, I'm sorry, I'm going off track, but knowing what you're going up against helps a lot too. This is an HTTP server, so knowing the protocol and knowing how things work generally help a tremendous amount. So, if you're not familiar with some bug you're looking at, it's in SMNP or something, read for a bit. Read some RFCs, go online, read some tutorials, and understand how the protocol actually works before you go about trying to track down the bug, because in the long run, it's going to help you far more than just cracking it open in IDA or starting doing runtime analysis in Ollie. If you know the protocol, you know how things work, you know the way things should be, and then you can use your cognitive ability that you have and figure out what's going on. So back on track. This is it says insufficient buffer boundary verification, copying user supplied data. Be it that it's an HTTP server, I'm going to deduce that a good place to start is probably a GET request, because that's the most common thing an HTTP server is going to see. It's going to say, get me this web page, get me this file, something. And I just think that's a good place to start. Like I said, knowing the protocol helps a little bit. So we're gonna open Minishare in IDA here. And I have it already in my demo directory. I have it installed, but I copied it here. I like copying the executable. I don't know why. I just like copying it to a different directory and working on it instead of just working on it where it is. I don't know. That's just me. So we're going to open this guy. Pardon? You think I'm that dumb? Jerks. Of course it isn't. Don't use this piece of trash software, by the way. I hope no one here wrote it, did they? All right, sweet. You're a liar. Drink. Okay, so it's a portal executable Windows file. We're going to hit OK and go. This time we get some error that says some important functions were not visible. This happens because the blah, 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 blah. Sure, okay, whatever. And it's loading the database, and this is a decently big program. And the first thing you see is it took a very short amount of time, which usually worries me. And B, if you look in the names and strings window, there's very little there. And you get instructions and you see things, but it doesn't look like what it should. And this is just off, doing this over and over and over and seeing and opening a bunch of things in IDA. I'm going to cheat a little bit right off the bat, because you see over here in this view, it says UPX1, and UPX is a packer, usually used to decrease the size of an executable, so people can download it faster and whatnot. This is why it's messed up. You don't know what's going on, and there's this really cool program, and I don't know who wrote it, but it rocks. Called PEID. Has anyone ever used this? It more or less will give a very good deterministic answer to what it thinks an executable is packed with. So we're going to open this guy and look at a file here. There's Minishare. Okay, and it's verifying what we thought. Ooh, cool. It says it's packed with UPX 0.89.6, and UPX is used a lot in non-malicious situations. People putting their HTTP server out there for people to download. Whoa, that's the guy from yak.net. I know him. He gave me a shirt way back in the day. How's it going, dude? That rules. I lost my shirt years ago. If you have another one, I'll buy it off of you. That would rock. Oh, sweet. I used to wear that shirt like every day. But like I was saying, now if you have some type of malware, it's usually packed with something not as commonplace as UPX, which is the universal packer. That's its name. But since this is non-malware, after we see UPX and IDA already knows, and then PEID said it's UPX. We can pretty much safely assume it's UPX. We don't have to worry too much, and you can download UPX for free off the internet. I'm going to make a copy of Minishare, and I'm going to call it Minishare Unpacked.exe. That's not a command in Windows. Okay. And then I have the UPX executable, which it's open source. You can download the source and you can download the executable. I've compiled the executable already in, and so we can use this. You see, okay, there's D, so we're going to decompress. D, Minishare. Looks like everything's cool, unpacked one file. So now we'll open IDA again. I really hate this window. And we're going to open up Minishare. Okay, default, whatever. This looks much better because, again, you see in the names window, you see send and get host by name. Those are real functions. You know it did something, and it's already done. So we can safely say now that we've successfully unpacked this executable and open it up in a disassembler. And now what we're going to do, I have my notes here, is we were talking about how I think it's going to be a overflow in a GET request. And the easiest way an executable will find where a GET request would be, as you think programmatically, they're going to search for the string GET somewhere and then break that chunk off, and then you'll have your actual request, and then it should be http/version/r/n/r/n. That's just how HTTP works. It's specified that way in the RFC. So we're going to look for this, and I'm going to sort these by alphabetical, and we're going to type GE, and you see the first thing we see there is a string in this binary that is the phrase GET. If you hit enter on this, it takes you somewhere, and you can hit Control X. You can do it in the options view, but I actually don't know how to do it that way. And then you see we're in really good shape. One cross-reference, which means there's only one place in this executable that references this memory location, which holds the string GET. So this is by the way, this very rarely happens. Actually, I'll show you something now. You can go to the imports, and this is the functions it imports from other DLLs, and it's commonplace that you see these are your standard C functions, and you can go to string copy, which again you might think that adding a binary is that easy. Find unsafe function calls, do cross references, determine if it's user input. Bam, you just got yourself on bug track, homie. But when you do a cross reference to this. Oh shit! Fuck! There's supposed to be like 1,000 of them. Okay, I'm way off. Actually, go. Yeah, there we go. There's a lot of calls to stir copy in this binary, and it's just not time effective to go through every one of these. And this is a small program. Think about trying to find a bug in, say, a Windows provided DLL. There's going to be 100 times more function calls to this function than there is in this small HTTP server that some guy wrote. So it's just not viable to do this. And maybe sometimes you have to, but there's usually better places to start. But you learn that as you go on. All right, where were we? Okay, we found our GET string, and awesomely, there's one cross-reference, so we hit OK to go there. And, okay, well, it send message A, does something, blah, 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 a bunch of assembly. But this is where it's moving something to EDI and then doing something. So I would safely say, and you see it's get space. So they're definitely, it looks like they're trying to tokenize a string. So getting little chunks of it everywhere. So what we can do is to verify this, we're going to copy this memory address, and we're going to start this crapware. Oh, sweet. Do you see the file that I'm sharing, Tom? It's one of Halvar's slides. I forgot to kind of explain what I'm doing here. I start up the program, and you can start Ollie. And Ollie's cool because it will let you attach to a process. Our web server is already running. We're sharing one file. Please no one hack me during this. I'm just trying to show you. Please no one hack me during this. I'm just trying to run it and give a live demo for Christ's sake. If I do, I'm really going to be pissed. And I will go home and I will write about it in my My Little Pony diary, and forever you will be in there, and you will be a bastard. Or bitch, because there's some women here. I'm an equal opportunity slanderer. Okay, so we got Ollie open, and we're going to look for mini share, which is right here. This process is running, and we're going to attach to this guy here. Ollie does stuff. It stops. You want to set your breakpoint before you actually run the program, because, I don't know, Ollie's weird. Sometimes it doesn't stop, break at the breakpoint that you set when you don't set it when it's paused. Don't ask me. I didn't write it. But it does rule. So you can hit Alt-G, and you go to a memory location. And, well, that's the same thing we see in IDA Pro, is this assembly here saying move that string to EDI, blah, 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 blah. So we hit F2. That sets a breakpoint on this guy. And we're running. I hit the run button. So we need to test this out. And I really like Python. It sucks that they control your white space. I have no clue why it was like that, but it makes me amazingly pissed off. Because if you accidentally hit a space somewhere, your script won't run, and it's stupid. But, yeah, what's that? Oh, really? I would hope so. I downloaded their environment here called idle, and at least it puts all the correct spaces and crap in for you, so you don't have to like space or tab, and that helps. But if they fix it, that rules, because I like Python. It's very intuitive to me. I did a lot of C# programming before, and someone was like, oh, you should write this script in Python, and I didn't know a stitch of Python. I didn't even know what it was. I knew it was a scripting language, but I never dealt with it. But I got it and was like, oh, okay. I just started writing things in it, and it worked. So I don't know. I like Python. To me, I know I'm going to piss a bunch of people off now. I think Perl is all clicks and whistles and bangs. I see so many $signs and symbols. I'm like, ugh, why? Why would you hate my... Yeah, I know. Luckily, I'll be drunk, so target you what, buddy? Yeah. My brother's a dentist, too, so feel free to knock some teeth out. I'm sure he'll repair them for free. I crafted this little Python exploit here, and you see it's only like 20 lines, and it's cool. And don't get me wrong, I've programmed in C a decent amount, and it's very good, and C's cool. But for rapid exploitation development, you want something that's fast and quick, and you don't have to recompile it. You can change something, hit save, and run it again, and it works, and it goes. That's why I like this. Or Perl, or you could use Perl if you're an asshole. I don't know much about Ruby. Okay, sweet. Or use Ruby. Cool. You see here, all I'm doing is setting up a socket to port 8080, which I have this thing running on, and I'm saying git, and then 61, which I believe is capital A. Hex 61 is the ASCII code for capital A, and then /r/n/r/n. So that's how you will hold terminate your request. We have the breakpoint set. We have our exploit here, and so what we'll do is we'll run this, and you can hit and hope it hits our breakpoint before it dies. And we'll hit F5, and that runs it, and we're fucked. You see access violation when executing 616161. Well, obviously we sent a bunch of hex 61s there. We overwrote the return address. This thing's owned. If you have shellcode there and knew what you're doing, this is definitely ownable. But if you're just trying to figure out how the hell it works and how big the buffer is, well then you got to go in more. So that obviously didn't work. And this is where I was saying knowing the protocol helps you a great bit, because we didn't see any response when we put git in there, but you know that every request is going to end in /r/n/r/n. That's just how it works. It's in the RFC. So hopefully we can find a string in here somewhere that is that. And there you go. We have this right here, and that's /r/n/r/n. One cross-reference, so we're money, baby. And you see it's right here. They move it into EDI, which is one of the registers, and do some stuff. Again, this is interesting. You see that they're putting /r here, and then string talk. This is a tokenizer. It's trying to break a string into pieces. Knowing C programming when you're doing this, or C++, helps a great deal. I'm pretty sure you actually couldn't do it without knowing C or C++. But this looks real interesting, you see, because you have a tokenizing string, it does some stuff, it calls another function here, which we'll go look at. Does some comparison. Now test EDX. EDX is usually used to make sure that the function that was just called, or the action just happening, is valid for the most point. So we go here, and this is what we like to see. You see ASC time, string copy. It's an unsafe function call to make, and you have to take that into account. Shit, what's our time looking like? I'm gonna skip this part. I know for a fact that this is not where exploitation occurs. This is something they set up to do a timestamp, as you see here. But the moral of the story is you found a place right here at this memory address that this is an awesome point to set a breakpoint, because you're into some unsafe function calls. You believe you found a place where you could go, and we're going to keep moving down the addresses. And don't, when I was first learning this, people did this, and they're just scrolling everywhere. You don't have to read line-by-line assembly. You find interesting pieces and places for you, and you go there. Especially with Intel, they have so many instructions. I don't know what some of them do. There's two PDFs that is their developer's manual, and have those on hand at all time. They list every instruction, what they do, and what values you can pass there. And it's literally the best resource for any assembly ever. Like, I think actually learning assembly, even to write it through reverse engineering, is easier than sitting down and reading like The Art of Assembly. Does anyone? I've read that one before. Yeah, it's really good. But I like looking at code and being able to run it and have the real source code. And you'd be like, oh, okay, I see that these 10 instructions actually copy a string here and do something to it, than just typing out assembly. Because I'm going to go off because we only have a few minutes, but I was in college, and it was the first year, and we had an assembly class, and at that point I wasn't really interested in that sort of thing. I was more interested in like doing bong rips and playing PS2. But we had this class, and we had to write these programs, and it was all in MIPS assembly. And it's a reduced instruction set architecture, which means there's not many instructions to do things with. And we had these projects, and I handed mine in because the Solaris machine that held all the user accounts for the university was vulnerable to this wet exploit. So I would just wait for someone else to do it, and then break into the server and steal their program, and then hand it in to my professor. And eventually he found out what I was doing, because he called me in and said, I know you can write these. What are you doing? I was like, nothing. I'm writing them. He's like, no, you're not. And he did a comparison of the programs. I changed some things or whatever. And he's like, no, it's effectively the same program. It's like, why are you copying? I was like, well, not really copying. I'm actually just breaking into the machine and stealing someone else's program and handing it into you. He's like, I'm not going to kick you out of my class. Just write your program next time. So that ruled. Well, the moral story is every university, they do availability over integrity any day. Universities are fun to play on. And there's very little repercussions usually, especially when you get... am I a student there? Yeah, exactly. Or when you're a student there and you actually work for the IT team, you can just be like, oh, after that happened, there was a security ticket that came up that said, investigate this person's IP, and I looked, and it was mine. Delete, see ya. It was great. All right. Exactly. I'm stress testing Samba. Yeah. All right. We're going to go on here, and I know I don't have much time, and I kind of just want to finish this up and then take a few questions. But as we go down here, I'm going to, like I said, I'm going to cheat. This is, again, sprintf is another thing you want to look out for. It's vulnerable. It doesn't do balance checking. You can put more data into a buffer than it was designed to be put there. Yeah, the essence were awesome. This right here is the vulnerable function call. Like I said, just for time restrictions, I'm going to tell you this is it. And you see the first thing they do is they move something into EBX, which is a stack variable. And be it that this is a stack-based buffer overflow, really good candidate. And you have to know the order in which things are done here. They're not on the stack this time. They're actually just loading them, as you see, to memory locations. They're moving the value of ECX into this memory location, and so on. But, I said, time constraints, they're moving this thing into EBX. And it's at var 718, and you can enter on this, and all it shows you the stack. You open my favorite Windows tool, which is Calc, and you go to the hex view, 718. Okay, we effectively have our magic number. 718 hex is 1,816 decimal. That's how much space you have between your variable and the return address on the stack. You're writing down this way effectively to the return address. This could be a good way to write an exploit or a signature, but I personally like doing it in runtime real quick just to make sure. Like, I like to see it happen. A, I'm a nerd, and B, it gives me that little bit of assurance that my math was right, I did everything correctly, and you get to see. And this one is a very good example why I do everything in runtime after I determine how big the buffer actually is. So we're going to copy this memory location here. And by the way, I just copy is Control Insert. How retarded is that? You can't hit Control C because it doesn't copy things. What's that? Okay. Shit. We're going to go. All right. Our server started here. We're going to attach to it again. We're going to go to the memory location that I copied. We can see it's the same thing. We're going to set a breakpoint. We're going to run. We're going to send our exploit again. It broke. And we can see that they load some value into EBX. And if you right-click on this guy, you can follow in the dump. And this is going to show you what's happening. And if you look at this window here, you're going to see when the overflow actually occurs, which, again, for me, when I started doing this, this really made the difference. Like, you visually saw something, and you were assured of it. So we're going to single step through this. It calls sprnf. This happens more than once, sorry. There we go. Now we see our string up here. That's what we said. It's lowercase a's, I'm sorry. EBX. And we're looking at this memory location down in this window. Bang. And you see it's copied. And if you look at this also, we've followed it, we can see it in the stack. Boom, our stack is munged. You see 6 ones everywhere. It's the stack's screwed. But the funny thing to look at this is, you could write a signature that says if you see anything over 1816, then it's bad. But the way they do this is they write. The funny thing about this is it's not actually an error in the actual program. It's an error in their logging that got them owned. You see Saturday, October, something. So not only is it you can send less than 1816, you have to find out the exact amount, and time restrictions restraining, it's 29 characters from here until they start writing the address there. So you can subtract that, and that's really your magic number. 1787 will write you to the return address. 4 more bytes over that, you overwrite the return address, and you successfully exploited the program. I'm sorry if this went a little bit too fast. It's a lot of content, but I hoped I tried to teach everyone something. Getting started is really hard. Don't give up. Just also don't be too stubborn to ask for help. Wow, you finished your 40 in my yes. And that's it. Any questions? Sweet. Question: why do you hate old people? Because they're lame. Does anyone watch The Office here? That was the 2 episodes ago when Creed dyed his hair black, and he came in like Michael asked, "Why do we hate old people?" And Creed was like, "'Cause they're lame." And that's an ongoing joke. But thank you very much.